Welcome to my channel. Today we look at Coplanar vectors. So we begin by defining Coplanar vectors and say that these are vectors which lie on the same plane in a three-dimensional space. It's important in this video to know how to determine if vectors are coplanar. So if vectors are coplanar, what we'll be doing to determine if they are coplanar is to see if their scalar triple product is 0. So if their scalar triple product is 0, then we say that the three vectors are coplanar. That is one way. And the other way is that we can tell if vectors are coplanar by seeing if one of the vectors can be expressed as a linear combination of the other vectors. So we look at these two ways. And of course, you can also use the knowledge of finding the determinant. And if the determinant of those three vectors, that you just extract the coefficients of those vectors and form a matrix. And if the matrix will be of determinant 0, then it means that those three vectors are coplanar. But I'll stick to the two methods. One, the method of finding the scalar triple product, if it is 0, and two, the method of finding out whether one of the vectors can be written as a linear combination of the other vectors. So let's go straight to the first example, and it says, are the following vectors coplanar? So the vectors are alpha, beta, and mu. So the question is, are they coplanar? So I'll use the first method, and what the first method says is, I get the scalar triple product. And if you do not know how to get the scalar triple product, you can check our previous videos, and we did that. We showed how to get the scalar triple product. So let's determine the scalar triple product. That is alpha dot beta cross mu. You can also get, you can get beta dot alpha cross mu, or you can get mu dot alpha cross beta. It's no problem. You can find any of that. But if these vectors are coplanar, each of those would give us 0. But if they are not coplanar, then they will not give us 0. So we extract the coefficients 4, 5, 6, 4, 5, 6, and then 1, 2, 3, and then 7, 8, 9, and find the determinants. So I use the easier way of finding the determinant. I carry the entire matrix as it appears there and place it here. And then take the first two columns and add them here. And then you notice that we have three diagonals running from left to right. They're in blue. Multiply along these diagonals as you add the result. So this will be 8 times 9, which is 72. This will be 15 times 7, which is 105. So I'm adding those results. And this will be 48. And then you also realize there are other diagonals running from right to left, top right to bottom left, they're in red. Multiply along these diagonals and subtract the result. For instance, this one gives us 45. So I subtract 45. This other one will give us 24 times 4, which is 96. So I subtract 96. And this other one will be 14 times 6, which is 84, so I subtract it. And when I do this, I find 0. So this scalar triple product is 0. And since it is 0, we say that the three vectors that were given are coplanar. Let's look at another example. And the example is, determine if the following vectors are coplanar, and these are the vectors alpha, beta, and mu. So I'll use the scalar triple product again. I find the scalar triple product, so that is alpha dot beta cross mu. And so I just extract the coefficients. I have for alpha, I have 2, -3, 5, 2, -3, 5. For beta, I have -4, -4, 7. And then for mu, I have -1, 3, -2. -1, 3, -2. And so I carry the entire matrix and place it here because I'm the determinant. And you can use another method for finding the determinant, but this is the easiest. So I carry the entire matrix, place it here, and then the last two columns, I add them here. And then notice that we have these diagonals in blue, the ones running from top left to bottom right. Multiply along these diagonals as you add the result. So this will be 2 times -4 times -2, and that gives you positive 16. And then this, the -3 times 7 times -1 gives you positive 21. And then 5 times -4, that is -20, times 3, that is -60. And then we have these other diagonals in red. They are running from top right to bottom left. Multiply along these diagonals as you subtract the result. So -3 times -4, that is positive 12, times -2, that is -24. So when I subtract -24, I get positive 24. And then this other one gives me 42 subtracted. And this other one gives me positive 20 subtracted. So what I get is -61 when I work out all this. So -1 is not equal to 0. And that means the scalar triple product is not 0, which means that these vectors are not coplanar. So the first two methods we've used, the first two examples we've used the knowledge of the scalar triple product. And in the following example, I want to use the method of seeing whether one of the vectors can be written as a scalar multiple, no, as a linear combination of the other two vectors. So let me begin by this example, and this example says determine if ABC are coplanar, where A is given by this, B is given by that, and C is given by this. So we use the second method. I want to see if, for instance, A can be written as a linear combination of B and C. That's what I want to see. And we know the definition. That if A is written as a linear combination of B and C, then it means we can obtain scalars X and Y, such that A can be written as X times B plus Y times C. And this is my A. X times B plus Y times C. Expanding that gives me 4x plus 2y is the sum or equals to 2. And then 3x plus 8y equal to 3. And then lastly, 7x plus 10y is equals to 5. Of these three equations, which I can now solve for x and y. And there are various ways of doing this, of solving for x and y if you're given a system of equations. But I'll choose the easiest of them all, where I want to use equation 3 to make x the subject of the formula. So if I make x the subject of the formula using equation 3, it means x would be the same as 5 minus 10y divided by 7, or 5 over 7 minus 10y over 7. And then from there, I substitute this x in equation 1, where there is x In equation 1, write this and then find y. Then find y. That's what I did. So when you do that, you would then find that y will be 3 over 13. Let's just see, but you can confirm that later, but let's just see. So what we have is 4. What was x? X was 5 out of 7 minus 10 y out of 7. And then plus 2y is equals to 2. So you want to get y. So opening this bracket, what I get is 20 out of 7 minus 40y out of 7 plus 2y is equals to 2. So I can carry this on the other side and leave this on the other side. So if I leave this on the other side, there is only 7. And this will be negative 40y plus 14y. And on the right side, I'll have 2 minus 20 out of 7. So what do I get? On the left side, this is negative 40y plus 14y, which gives me negative 26. Negative 26y out of 7. Now what about the right-hand side? The LCM is 7. And this will be 14 minus 20. 14 minus 20, that is negative 6. And so what is y? Y is negative 6 out of 7 times negative 7 out of 26, where 7 cancels, and this becomes positive. But it's positive 3 out of 13 when you divide by 2. So this is y, positive 3 out of 13. Now, after obtaining y, you come to this equation, substitute 3 over 13 here for y, and get x. So when you do that, x becomes 5 out of 13. So we have the two values of x and y. Since we've not used this equation, the second equation, you can try and see whether the two values are correct. So that would be the work of this second equation. So you put the value of x, or the x that you have here, and the value of y that you have here, and see whether you obtain 3. If that happens, then it means that x and y as obtained are correct. In some cases, they may refuse to be correct. So it's always good to try and verify. So don't assume that once you've gotten x and y, they become the values. It's always good to verify. So I also did my verification. And after doing my verification, I was convinced that the values of x and y as obtained were correct, which means that A can be written as a linear combination of B and C this way, or divided this way. And so since A can be written as a linear combination of B and C, we conclude and say that the 3 vectors given to us were coplanar. Otherwise, if it will not have been possible to write A as a linear combination of these other vectors, then we would say that the vectors were not coplanar.